Welcome to the final module of Six Sigma Yellow Belt training. This will cover the improve and control phases. I'm a certified Six Sigma Black Belt with the American Society of Quality, and I'll be conducting your training. Here we see a one-page summary of the DMAG method. We went over this in the beginning. You should now be able to look at this and get an idea of why these important concepts are on this one-page summary. We're covering the improve and control in one phase. Improve and control phases are highly related phases. Let's go over some review of basic improvement techniques. A Kaizen is a term from the Lean, as it's come to been defined by the Toyota production system. It means continuous improvement. As a leadership management role in this, it means promoting and implementation of incremental, small manageable improvement by everyone on a never-ending basis. One of the things that demarcates Kaizen is that it's improvement by everyone, a culture where everyone believes in improvement and are empowered to come together, being the workers that know the process, to propose best practices with an expectation that leadership will listen to them and implement them. It's methodical, patient, persistent improvement to eliminate all waste and non-value activity. Kaizen Blitz, also known as a Kaizen workshop, also known as a rapid improvement event, is where you spend 2 to 5 days a week to do an improvement event. Usually these improvement events, these Kaizen workshops, the black belt or the lead will spend several weeks ahead of the workshop putting together, preparing the charter and getting the team together, getting a champion, getting some data together, and then usually the format is something like you first analyze the current state, use different tools to brainstorm to come up with improvements to the current state, evaluate and select these improvements, and then you put together an implementation plan and get buy-in from the stakeholders, usually on the last day. Usually after the Kaizen event, let's say it's a 4-day event, usually the afternoon of the 4th day or the afternoon or towards the end of the last day of the event, you bring leadership together and you have a workshop report out. And then you spend the next you come out of those workshops with the improvements and implementation plan. Over the coming weeks or months, you implement them, and your improvements should still have a control element to where you've checked and act on the improvements to make sure that they went in place as intended and are achieving the intended results. And then you move from one Kaizen to another, continually improving. So these are good supplements projects to longer-term Lean or Six Sigma projects. Many times a value stream map is used in the current state to walk through the process for collecting data. You identify Murray and Muda, you identify waste, burden, leveling of the flow, and barriers to making sure the flow is balanced and fluid without waste. You improve the current state conditions with management to form a future state, and that's why management should know that they're coming together to hear what you have to say, and you should have high expectations. Management will be receptive to the team's findings. Improvement techniques. PDCA is an alternate acronym for DMAG. It's called a Deming or Sheward cycle. It's a 4-step model for carrying out change. This is all continuous improvement, Kaizen, whether by any other name. It's never going to. It's every day, continuously. You can use plan, do, check, act in the same way you do DMAG. It's a model for continuous improvement. When starting a new improvement project, when developing new or improved design, when defining a repetitive work process, when planning data collection. It's just a methodical acronym for the scientific method. Plan, recognize an opportunity, and plan a change. Let's define it. Do it, implement it, test the change. It's always standard procedure. So when possible, you test a pilot or a small subject matter area before moving on to a larger, more intense production environment. Check and review, make sure items went in as intended, and then have a plan to act when you find that things aren't working as you have expected. As we discussed before, in your charter and as part of your project, you should always try to do a cost-benefit analysis, understand what you've saved in COPQ, and put your benefit in terms of dollars. If you work with financial representatives, they may even help you with more sophisticated methods of estimating benefit to a project from your improvements. This is an expected value technique, and here's an example. You can work through it on your own if you desire. I think it's unlikely at the yellow belt level you'd be required to do an analysis like this on your own or be tested on it in any great detail. Just be aware that certainly expected value for an improvement project would be an option for quantifying to the financial community and to executives what benefit from a project might be. Similarly, you have a net present value or internal rate of return calculations that can help you with return on investment from a project, benefit calculations for a project, that financial people may wish to have developed and would be interested in at the executive level and the accounting level. Here's an example of the net present value method, which you could look at as time allows. This method converts all future cash flows to today's dollars at a specified interest rate. Here's an example of a cost of poor quality worksheet or putting together your return on investment of your project. This is typical. Your COPQ worksheets can vary greatly depending on your situation, what management would like to see, the level of rigor they'd like to see in estimating the benefit. So this is very typical, and it could also have many variations. This is actually a canned worksheet that's in a QI Macros, which is a Excel add-on statistical analysis software package. When you compute total costs and benefits and put them in some type of table or decision matrix or matrix that shows impact versus effort as part of your final solution to the decision process, do make sure you try to include as many costs and benefits as you can, not just the ones that may be directly resulting from improving the primary metric and secondary metric, but try to capture all costs and benefit in totality to the maximum extent possible. Cost benefit analysis, when you're deciding on improvement solutions to proceed with, you may use simpler methods such as the payback matrix. That is a graphical representation of where an idea or a group of ideas fall on a continuum with respect to how hard it is to implement versus the perceived payback in the results of the project. Now, after you've decided on your improvements and you've satisfied you want to implement them, you need to put all the tasks, of course, of your implementation into some plan or form. A Gantt chart is certainly a standard way to execute an implementation plan, or a PERT chart, or even just an Excel table outlining who, what, when, where you need to do things and how you're going to do things. You may want a pilot. You may certainly want to do a force field analysis or barriers and aids to make sure that you're thinking about what might be the barriers to the future state. You may want to do an FMEA to see where your improvement plan may have pitfalls you want to strengthen. You've got to consider work instructions and policies and procedure changes, changes in measurement systems, calibrations. You may need to do a new measurement system analysis, and you certainly want to be sure your training and communication plans for the new future state are in place. Now, oftentimes you'll want to do a pilot or equivalent of pilot on an implementation where you do the changes on a small scale, where any negative results are reversible or minimized. It's incremental, it's lower risk to production, and also in lieu of pilot or in addition to, you can use simulations. Of course, after the pilot, you'll want to take lessons learned and adjust the procedure. Now, there are three basic pillars to implementation. Some kind of map or blueprint of the future state, some kind of work instructions so that you can achieve the future state by using the people involved in the process, and a control plan. Now, the control plan verifies that things went as expected and validates the process. In other words, verifies, demonstrates that you're getting the intended result of the new state, and gives you data for a final assessment of the benefits, hopefully translated to dollars. It's ongoing monitoring of the new state to flag problems. It's the way that the improvements get institutionalized and you hold the gains. A primary tool of the control phase and a primary part of many control plans are control charts of the critical to quality characteristics of interest. Now, while they're a key player in control phase and control plans, you don't always have a control charts, and there's more to the control phase than simply control charts. Potential aspects of a control plan are an action plan or Gantt chart or other checking tools to check key aspects or control or gauge points of the future state. Some kind of plan to audit and check on the future state, make sure it's working as possible, as intended. Certainly, SPC or statistical process control methods is always something that you would like to try to put in place if it's applicable. You're going to have configuration, management, change control issues in your control plan and ongoing communication plans. Now, in your control plan, it's going to want to have established checkpoints or control points where you check and act on the process. These might be called gauge points. So your control plan should have areas in the process such as key significant points where you're going to check and have a prearranged determination of what kinds of actions you're going to take if it's not working as expected. You can often use a map to show gauge points. You're going to be using checklists and audit plans as you execute your control plan. So places to have checkpoints or control subject points at turnover changes of disciplines of departments and authority, at showstopper points where you have irreversible activities, at key metric data collection points you can have a gauge to make sure that you're getting your metrics, at key activities establish standard work or standing operating procedure, at key activities to the process owner and major stakeholders. The control plan should check things that view the process from a total organizational perspective. A classic control plan will identify who, what, where, when, and how, and why. Typical factors in a plan. What do you do if not in control? What are your feedback loops? Again, statistical process control is often a big player. You're going to use process maps, Excel spreadsheets that outline the key operational definitions of your control plan, and they're often employed. So you're going to have your process steps, what your control subject is, what your specifications or requirements are, what your control method is, what type of data are you collecting, what's your sample size, who's measuring it, how often do you measure it, What's your reaction at the gauge point if things aren't working? What's your plan to go and try to put the process back in an expected state, expected future state? All these things are typical items covered in a control plan. The exact nature or look of a control plan will be situational. Now, statistical process control is a big part of the control phase in many cases, and let's go over that. It can be done by hand or programmed in Excel. However, this day and age, that's highly unlikely and rather brutal. Your best bet is to use statistical analysis software. Now, as we mentioned before, control charts are basically a time series XY plot with significant features. Examples of some analysis software that can help you with SPCs, Minitab, QI Macros, Statistica, SIGMA-XL. Statistical process control is a method of quality control which uses statistical methods to monitor critical to quality variables to assist in process adjustment decisions to control the process for optimal operation, effectiveness, and efficiency. It was developed by Walter Schuhart in the 1920s. The identifiable inception was a series of lectures to the Department of Agriculture captured and published in a book called Statistical Method from a Viewpoint of Quality Control. This book, interestingly enough, was edited by Edwards Deming. All control charts, both variable and attribute, which are the two types, help you investigate variation on which to take action to improve your process without over-controlling it or tampering with it. Key to optimal control is distinction between common and a special, also called assignable cause variation. Statistical process control or control charts, one of the basic quality tools, perhaps most critical, especially when you consider it in all its forms, which includes really time series plots. Control charts identify stability in a present process or current state, which understanding how stable your current process is greatly influences your improvement strategies. You can identify gaps in current states worth pursuing once you have a stable process. During the improvement process, you can use control charts to identify the progress you're making. In a classical improvement project, you'd move from one steady state and down along about a 45-degree line along the critical to quality metric that you're measuring down to another plateau or stable state. Once you have a new future state, you can use control charts to document the improvement and to control the process and sustain the gain. Many ISO programs imply or infer that you would want to use control charts to keep your processes in a state of control as you incrementally continually improve. Used widely in industry and healthcare, and certainly can be used in service projects. The data set is considered stable when the absence of special causes is achieved. This is a state of statistical control, where variation is attributed to natural random process variation. Control chart is the best tool to search for special or assignable causes. Again, it was developed by Schuhart, and it's been a key part of improvement since its development by Dr. Schuhart. Random, common causes. Common cause variation is random, natural variation. Trying to eliminate common cause variation does more harm than good. It's called overcorrection or tampering. Likewise, mistaking special cause for common cause can lead to under control. Special causes or assignable causes are not random. They occur relatively infrequently. They're aberrations, they're atypical, they're unusual abnormalities. They're not intentionally part of the process, and we can likely assign a cause with minimal investigation when we find special cause variation. It's important to try to find and eliminate special cause variation. That's key to improving a process. This is an example we went over in the analysis phase discussion, so I'll leave it to you to read this again when you'd like to take the time. Trends and patterns can also signify special cause. When all data falls within control limits without special cause, trends or pattern, again, is considered a state of statistical control and random variation. Special cause variation can be identified by points being above the upper control limit or below the lower control limit. This is probably the most straightforward, simplest identification of special cause. And also trends or patterns or other statistic patterns and trends that cannot be shown statistically to be random will flag special cause, and we'll go over those here shortly. Again, a process is stable but does not contain any special cause variation, and only common cause is present. This example here, the process is stable because it appears to be distributed randomly and does not violate any of the 8 control chart tests that we'll go over. In particular, you can see that all points were within the control limits, and as we'll see, those other tests are for trends or patterns that statistically are shown not to be random. We see there an example of a process that is not stable because it's exhibiting some common cause variation, and that trend upward there is a case of a trend that is not common cause variation. Now it says here a process must be stable before its capability is assessed and improved, or improvements are initiated. That's some debate on that. That's a little bit strong. There's some practitioners who say that it's vital that the process be stable. There's other practitioners who say you can make judgment about the process with respect to if it's adequately stable to suit you for your improvement. I'd say it's situational. I don't like absolutes. Most black belts I know like the phrase, it depends. It seems like it's a universal answer to any question you get in Lean Six Sigma. You could just say it depends. Well, it depends. It doesn't have to be stable. It's not some rule or law. It's just strongly advised in many cases to stabilize your process first before moving forward. Now, here is a summary out of Minitab. It's a good summary, and you can read this when you have time. It goes over many of the standard accepted rules for determining if you have special cause variation. These rules are checked by statistical analysis within software to see if it's meeting these standards for statistical demonstration that it's not random natural variation. And for attribute charts, there's a few less rules, but the rule is when you're doing attribute charts, which is a time series plot control chart for data that is not continuous, you have it's analogous with slightly different charts as we'll go over. So here we have some typical output for this is continuous data. This is called an individual value chart. We'll cover that a little bit. But you can see this, particularly when you use statistical analysis software, which is probably recommended highly these days, and you turn your tests on, it will flag special cause variation for you. So you see here we have red dots everywhere. We have violations of common cause variation, and it gives you a little summary of why it flagged those points. So you'd want to ideally eliminate all those red points before you said that you had a stable process and were ready to improve it. Here we have the fundamental equation of SPC, where X is a sample quality characteristic of interest. The mean of the sample distribution is mu sub x, and the sample standard deviation is sigma sub x. then the upper control limit is equal to the mean of the sample distribution plus 3 standard deviations, and the lower control limit is the mean minus standard 3 deviations, with the center line being the sample mean. Now, 3 standard deviations is not a mathematical threshold. It's a historic and accepted standard for identifying the zone of common cause variation. It implies that data outside of 99.7% of all the data will likely be assignable. Other limits can and are used, but 3 standard deviations is widely used and generally used unless you have some specific reason not to. Now, standard deviation of the sample is not simply directly calculated from the mathematical equations of variation for SPC charts. Standard sample size specific constants or control chart constants have been developed that use the sample range to calculate an estimate of the standard deviation. This gives increased accuracy for a given sample size. These constants can be easily found in any reference table on statistic process control, but generally, again, nowadays you'll be using statistical analysis software which will take care of using the anti-biasing constants for you. Control limits define common cause limits and must not be confused with specification limits, which define the product acceptability in the eyes of the customer. Here we see a distribution where we have the upper and lower control limits plotted, 3 standard deviations, and we see a customer implied lower spec limit and upper spec limit. So anything beyond the red dashed lines would be defects. So we have here a case that is undesirable. We have a process that is in a state of statistical control where it's meeting its upper and lower control limits, but it's not going to tend to meet upper and lower specification limits because they're inside of the upper and lower control limits. So we have specification limits that are requiring a tighter variation than the process presently is really achieving in a steady state environment. Now, the basic SPC methodology is to select the appropriate quality characteristic to plot, so you're going to be monitoring a characteristic of concern, establish an appropriate sample size and rational subgroup. You're going to select the appropriate control chart to use, and then implement a random data collection plan where every sample has an equal chance of being selected. You're going to calculate the center line and control limits and check for assignable cause. Recalculate the control limits if the process changes. A flow chart of this, if it's variable data and you're using subgroups, you're going to use an X bar R chart or an X bar S chart. If it's just individual data points, you're going to use an individuals and moving range chart. If it's attribute data and it's defectives per lot, you'll use a P chart or an NP chart. And for defects per unit, you'll use a U chart or a C chart. Subgroup selection must be logical or rational. The subsample is to detect piece-to-piece repeatability at a given time, independent of factors that occur over time from sample to sample. So it's a point estimate. Samples frequently consist of parts that are produced successively by the same process. The intent is to see consistency at a point in time for a homogeneous process. So you want to take samples that minimize variability. You want to take samples that should be showing you only what the variation is at that particular time for a process. For example, if a machine had 5 different stamping pistons, you may well want to take the samples all from the same sample piston. Otherwise, you'll be introducing piston-to-piston variation along with the over time variation as you move forward sample to sample. Here's another example of subgroup. Again, a group of units produced under the same set of conditions. Subgroups or rational subgroups are meant to represent a snapshot of the process. Therefore, they must be taken close together in time and in a manner that should represent a homogeneous sample. But they should still be independent of each other. For example, a die-cut machine produces 100 plastic parts per hour. The engineer measures 5 randomly selected parts at the beginning of every hour. Each sample of 5 parts is a subgroup. Subgroups help separate the two types of variation. If you take a subgroup close in time from what should be a homogeneous part of the process, the variation among the measurements within the subgroup you should find common cause variation. If you don't, you probably have some problem with the machine right there at that point. Now, the variation between subgroups is where you are more likely to pick up assignable cause from factors that have came into the process over time. Here's a plot of samples taken from the die-cut machine. Each vertical line of the gray symbols represents values in a subgroup. So that's the subgroup variation. The blue intervals represent the within subgroup variation. And the red mean connecting line connects the mean of the sample is the between subgroup variation. To improve process quality, you should make an effort to eliminate subgroup variation and reduce within subgroup variations also to the maximum extent possible. Control charts that use rational subgroups are the X-bar R chart or X-bar range chart and the X-bar S chart, which uses standard deviation. It plots the process mean and the process range over time for variables and subgroups. This combination control chart is widely used to examine the stability of processes in many industries. For example, you can use an X-bar R chart to examine the process mean and variation for subgroups of part lengths, call times, hospitals, patients' blood pressure, and so on and so on. If you were not using subgroups and each dot on those control charts was simply one data measurement point and not a subgroup of 4 or 5 or so, it would be an individuals chart and a moving range chart. The X-bar and R chart are displayed together because you should interpret both charts to determine if your process is stable. You'd want to examine the R chart first. The process variation must be in control to correctly interpret the X-bar chart because the control limits of the X-bar chart are calculated considering both process spread and centering. If the range chart or R chart is out of control, then the control limits on the X-bar R chart may be inaccurate. The X-bar and S chart is analogous to the X-bar and R, except it plots standard deviation instead of the process range over time. It still plots the same average of each sample group, but it now uses standard deviation of the sample to calculate variation. The standard deviation is a better estimate of dispersion for larger sample sizes, greater than 10. For smaller sample sizes, the range is better. If you're only taking individual values without taking samples, you can use an eye chart, individuals chart, and a moving range chart. Use this combination to monitor process center and variation when it's difficult to do group measurements. When data are collected as individual observations, you cannot calculate standard deviation for each subgroup. So the moving range, which is the difference between successive data points, is an alternative way to calculate process variation. Now this is attribute data. When your data is not variable data, P-charts are used, or proportion or percentage of defectives for a sample size. NP plots are a count of the number of defectives from a constant sample size. C-charts plot the count of numbers of defects from a constant sample size, and U-charts plot the number of defects per unit, again a proportion, where sample size can vary. So here's an example of an attributes chart. A test was conducted to find the presence of acceptable metal flakes in 6 samples of jugs of cooling oil. So we find the number of defective per sample, and we can plot that on a P chart, giving our proportion defective. If we use a constant sample size, we'll get a straight line. You can use an average sample size, or if you use the actual sample size for each sample taken, your upper and upper control chart there will vary as the sample size varies. The test was conducted to find the presence of acceptable metal. Again, this time we'll look at it as an NP chart. We see the number of defective per sample. We see this time the control chart gives us sample count equivalent to the count of defectives. And we see again, if you vary the sample size, you vary your upper control limit. And if you use a constant sample size representation, you'll get a steady, straight upper control limit. Here's a C chart. It gives you a sample count of defects, number of defective. That is always a constant sample size. U chart, sample count of defects per unit. So we have a number of defective per sample for a defective per defects per unit, and you can plot that in the control chart. Again, if you use the varying sample size, your upper control limit will vary. A control plan provides an institutional memory of the status of a process and the measurements that define it. It provides for timely process troubleshooting, repair, aids in training, and audit activities. The control plan, especially if we use control charts, becomes a living document as part of the document control, providing for identification, traceability, and retrieval of the improvements that go into establishing a stable baseline process state. The following should be used under appropriate configuration and control document control: process maps, product drawings, work instructions, support training, and the control plan. These being under document or configuration control is vital to establishing a current best practice process state that can be communicated to process participants, owners, and all other stakeholders.